All right, another series that we can find the infinite sum for is what we call a telescoping series. Now, to change the sequence to an infinite series, determine if the sequence will diverge or converge, and if it converges, then find the sum. So this special telescoping sequence is you need to see two fractions being subtracted. So you get this cancellation concept going on. So as we're going to list out these terms, what's going to happen is you create binomial terms, and then there will be a positive fraction in one binomial term, a minus fraction that's the opposite of that positive in some other binomial. We cancel them out. And it's like you're collapsing all these terms down to a very few terms, and then we can take the limit and we'll find the sum. So this is not a geometric series, but you will find the pattern of partial sums. So if I were to start listing out some of my partial sums, S sub n is going to equal, and I'm going to create a whole list, but looking at this is S sub 1. If I put a 1 in for n, 1 over 1 is 1, minus 1 over 1 plus 1, that's a 2 in the denominator. Then add the second binomial. Don't combine these together. That's the biggest mistake. You want to leave these two terms in a binomial format. So as you build all these terms, you're going to notice this pattern we're looking for. So when n is 2, you're going to have plus 1 half minus 1 third. Okay, now when n is 3, you're going to have 1 third minus 1 fourth. When n is 4, plus 1 fourth minus 1 fifth. Plus yada 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 all the way out to 1 over n minus 1 over n plus 1. Well, my first pattern is there's a minus 1 half. That's a positive 1 half. These are opposites. There's a minus 1 third. There's a plus 1 third. Cancel. Minus 1 fourth, plus 1 fourth. And these are going to keep canceling until you get to this term, which will be here in this previous binomial. And you're stuck with these two terms. So again, here's that telescoping concept. If you think a telescope, you extend it all the way out, and then you collapse it down to just these two final terms. That's my nth partial sum. Now, if I make it an infinite sum, then my n has to go to infinity, so we're going to take a limit as n goes to infinity. Well, again, this will approach 0 because the bottom's getting bigger faster than our constant. So this limit is a 1. That series converges, and the sum of this telescoping series is that limit value of 1. We can actually find that sum. Example 9. Okay, now here we got a problem. I don't have two fractions being added or subtracted together. So here I'm going to have to do my partial fraction decomposition. So this is going to be this fraction is going to equal a over n, the first factor, and then b over n plus 2. Okay, linear factors get constants at the top. All right, so if we multiply by the LCD right here to both these terms, you're going to get 1 is equal to a times the n plus 2 plus b times the n. That's multiplying this LCD to everything on the top so you can cancel out all the denominators. So we're going to get, okay, let's solve this. Let's let n equal 0. So we'll cancel this out. So that's a 0. Then we're going to get 0 plus 2 is 2. A is 1 half. You just solve for a. Now let's solve for b. Let n now be negative 2. So this becomes a 0, so 1 equals negative 2b. Divide over the negative 2, b is equal to negative 1 half. So rewrite this for this fraction. Well, again, we don't want numerators to have fractions, so let's factor the 1 half out to the front. And now it's 1 over n minus 1 over n plus 2. We have two fractions that are being subtracted, so this is going to be a telescoping series. So S sub n is 1 half times, let's put in a 1 over 1 minus 1 over 3 plus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 5. You just keep increasing each denominator by 1. Oh, that's plenty. That's a good chunk. But now here, just notice something. My minus 1/3 doesn't see the plus 1/3 until way over here. And I don't see a minus 1/2 anywhere. That didn't cancel. Minus 1/4, I found it here. So I'm going to start at the back and finish with this fraction and then subtract 1 from each of these denominators. So 1 over n becomes 1 over n minus 1. 1 over n plus 2 becomes 1 over n plus 1. Subtract 1 again. 1 over n minus 2 minus 1 over n. Subtract 1s again. Subtract. You're always adding the binomials together, but I'm going to find that pattern here. So as I start my canceling, those terms cancel. Negative 1/4 and 1/4 cancel. Minus 1/5, they cancel. They cancel. So everything's canceling except for those two. So as I get to the back, now here's something that's important. If two terms didn't cancel in the front, then there's probably going to be two terms in the back that didn't cancel. So these are going to keep going and canceling. So looking at the back end, 1 over n minus 1 over n, they cancel. Let's see, here we go. 1 over n minus 1, it's a negative. Here's the positive. They cancel. And, oh, here's my next one. They cancel. Okay, since this cancels here, this binomial, that means all my binomials will cancel the rest of the way. So it's 1/2. We have 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. That's my nth partial sum formula for that sum of those partial sums. Okay, but we want an infinite sum, so take the limit as n goes to infinity of this right here. Well, these will be zeros. 1 plus 1/2 is 3/2 times 1/2 will be 3/4. So yes, this series does converge, and its sum is that 3/4 right there. So those are our telescoping series.